what the James Webb Space Telescope is made of. If you step outside late at night, when the air is still and the world has gone quiet, the sky can feel impossibly deep. Even when it looks empty, it is not empty at all. Behind the darkness are stars, clouds of dust, distant galaxies, and faint traces of light that have been traveling longer than human civilization has existed. For thousands of years, people could only guess what was hidden there. They imagined the stars as fires, spirits, gods, maps, omens, or distant worlds. But over time, imagination was joined by instruments, and those instruments slowly became more powerful. The James Webb Space Telescope is one of the most extraordinary instruments ever created for that purpose. It was not built simply to take beautiful pictures, although it certainly does that. It was built to answer questions that are almost as old as curiosity itself. How did the first galaxies form? What were the earliest stars like? How do planets emerge around distant suns? And could some of those distant worlds contain the chemistry of life? At the center of the observatory is its enormous primary mirror. Unlike a traditional telescope mirror made from one large circular piece, Webb's mirror is divided into 18 hexagonal segments. These segments fit together with remarkable precision, forming one large reflective surface. Each piece is made from beryllium, a metal chosen because it is both strong and lightweight, and because it behaves predictably even in the very cold conditions of space. That matters because the telescope must remain stable while observing incredibly faint sources of light. A tiny distortion in the shape of a mirror can affect the quality of an observation. Each mirror segment is coated with a very thin layer of gold. Gold may sound decorative, but here it is entirely practical. The James Webb Telescope is designed mainly for infrared astronomy, and gold reflects infrared light extremely well. That allows the telescope to gather wavelengths of light that human eyes cannot see, but that carry crucial information about the universe. In many cases, infrared light allows astronomers to observe objects hidden by cosmic dust, or objects so distant that their visible light has been stretched into infrared wavelengths by the expansion of the universe. The mirror is large for a reason. The larger a telescope mirror is, the more light it can collect, and the more light it collects, the fainter and farther the telescope can see. For ordinary bright stars, this might not matter much, but for galaxies at the edge of observable time, or for a tiny atmospheric signature around a distant exoplanet, every bit of light matters. The telescope also contains highly sensitive scientific instruments, each designed for a slightly different task. Some record detailed images, some split light into spectra, so scientists can read the chemical fingerprints hidden within it. Others specialize in particular infrared ranges. Together, they make Webb far more than a camera. It is really a floating laboratory, one built to read the universe through light. What makes all of this so remarkable is not only the engineering, but the intention behind it. Every material, every reflective coating, every sensor, every support structure was chosen for a reason. The observatory is the result of thousands of decisions, each made in service of one goal: to detect light so faint and so old that without this machine, it would remain beyond our reach. Why NASA built a telescope that folds like origami. One of the most unusual things about the James Webb Space Telescope is that it could never have reached space in the shape it now has. If you were to see it fully deployed with its broad mirror and enormous multi-layered sunshield, you might assume it was assembled piece by piece after launch. But it was not. Instead, it began its journey folded into a much more compact form, carefully designed to fit inside the rocket that carried it away from Earth. This was one of the great engineering challenges of the mission. Scientists wanted a mirror much larger than the one aboard Hubble. They wanted a telescope powerful enough to gather ancient infrared light from the earliest galaxies. But rockets have limits. The fairing at the top of a launch vehicle offers only so much room. That meant the telescope could not simply be built at full size and launched as it was. So engineers designed it to fold. The mirror wings folded inward. The supporting structures were tucked into launch position. The giant sun shield, which now stretches wide like a reflective sail, was folded up in layers. During launch, the observatory looked more like a tightly packed machine than the graceful deep space telescope it would become. Once the telescope was on its way to its destination, the real tension began. Deployment in space is not like opening a device on Earth where a technician can step in if something goes wrong. The unfolding process involved a long sequence of carefully timed actions. Mechanical arms had to extend, protective covers had to release, the layered sunshield had to spread out and tension itself properly. Mirror segments had to move into alignment. Each of these events depended on motors, hinges, pulleys, sensors, and software all performing exactly as intended. People sometimes compare this to origami, and that comparison works surprisingly well. Like a folded paper form, the telescope had to transform from a compact launch shape into a larger functional structure. But unlike paper, every fold and release had to happen in the vacuum of space, far from human hands, under conditions where there would be no simple rescue if something failed. That made the deployment phase one of the most nerve-wracking parts of the entire mission. For years, people had worked on the telescope. A failure in deployment could have placed the entire project at risk. When the observatory launched successfully, that was only the beginning. Engineers then had to watch and verify each unfolding step, knowing that the telescope's future depended on hundreds of things working together. And they did. Step by step, the observatory opened itself to the cosmos. The sunshield spread into place. The mirror wings unfolded. The tower separating the warm side from the cold side extended. The machine that had launched in a compact shape slowly became the giant observatory it was designed to be. There is something beautiful about that transformation. It reflects the mission itself. A folded telescope, leaving Earth in silence, then opening itself little by little in the darkness, becoming what it needed to become in order to see farther than any previous observatory. It is engineering, yes, but it also feels almost symbolic. A device built to reveal the hidden universe first had to unfold its own hidden form. Why the telescope is almost 1 million miles from Earth. Many people are familiar with the Hubble Space Telescope and imagine that all space telescopes orbit near Earth in roughly the same way. But the James Webb Space Telescope was built for a different kind of mission and placed in a very different location. Rather than orbiting close to Earth, Webb travels around the Sun in a position associated with what is known as the second Lagrange point, or LL2. This region lies about 1.5 million kilometers from Earth, much farther away than the Moon. It is not a point where gravity disappears. Rather, it is a place where the gravitational effects of the Earth and the Sun combine in such a way that a spacecraft can remain in a relatively stable configuration while following Earth around the Sun. This location offers several advantages, and for Webb they are crucial. The telescope needs to remain extremely cold. Since it is built to detect infrared radiation, even small amounts of heat from nearby sources could interfere with its observations. If the telescope were too warm, it would effectively glow in infrared itself, making it harder to detect the faint cosmic signals it was meant to capture. That is why Webb carries such a large sun shield. The sun shield acts like a permanent barrier between the hot side and the cold side of the observatory. On one side are the Sun, Earth, and Moon. On the other side is the deep darkness of space. By sitting near L2, the telescope can keep all three of those bright and relatively warm bodies in roughly the same direction. That allows the sun shield to block them all at once. The result is a stable thermal environment. The telescope's instruments, protected in deep shade, can cool down to very low temperatures. This makes them sensitive enough to record faint infrared light from distant galaxies, dusty star-forming regions, and exoplanet atmospheres. The distance from Earth also changes the nature of the telescope's mission. Hubble could be serviced by astronauts because it orbited relatively nearby. Webb cannot. It was designed from the beginning with the understanding that it would operate far beyond the reach of repair missions as we know them. That added pressure to every stage of engineering, testing, and deployment. The telescope had to work because once it left, there would be no simple second chance. Yet there is also something elegant about its position. The observatory does not circle Earth like a companion. Instead, it keeps watch from farther out, moving in a quiet gravitational balance while staring outward into the universe. It sits in a place chosen not because it is easy to reach, but because it gives the telescope the silence and cold it needs to listen to ancient light. How Webb can see the first galaxies in the universe. One of the most astonishing things about astronomy is that distance is also time. When we look at the moon, we see it as it was a little more than a second ago. When we look at the sun, we see it as it was about 8 minutes ago. When we look at stars, we may be seeing them as they were years, decades, or centuries in the past. And when we look at extremely distant galaxies, we are looking so far back that we begin to approach the early history of the universe itself. This is possible because light takes time to travel. The faster nothing can go is still not instantaneous across cosmic distances. A galaxy billions of light years away does not appear to us as it is now. It appears as it was when its light began the journey toward us. The James Webb Space Telescope was built specifically to take advantage of this fact. Its infrared sensitivity allows it to detect some of the oldest light ever observed from distant galaxies. This is especially important because the universe is expanding. As space expands, the wavelengths of light traveling through it become stretched. Light that may once have been visible or ultraviolet can be shifted into the infrared by the time it reaches us. This stretching is known as redshift. The earliest galaxies in the universe are therefore especially difficult to study with visible light telescopes alone. Their light has been stretched so much that infrared observations become essential. That is where Webb becomes so powerful. It can detect the long, faint wavelengths arriving from structures that formed when the universe was still very young. To say that Webb sees the first galaxies is not to say it sees the absolute beginning of everything, but it does allow astronomers to look deep into the era when early stars and galaxies were forming out of the cosmic darkness that followed the Big Bang. In those observations, scientists can study how matter gathered, how stars ignited, and how the first large structures emerged. This is part of what makes Webb so exciting. It is not only extending our view farther in distance, it is extending our view deeper in time. Each ancient galaxy it detects becomes a clue, a piece of evidence about how the universe moved from simplicity toward complexity. And in a strange way, this can feel very peaceful to think about. The light arriving at the telescope tonight may have begun its journey long before the Earth existed in its present form. It crossed billions of years of expansion, silence, and cosmic change, only to arrive at a gold-coated mirror built by a brief and curious species on a small planet. The telescope does not rush this process. It simply waits, collects, and records. The galaxies that appeared too early. Science is often imagined as a process of confirming what we already expect, but some of its most exciting moments happen when reality refuses to behave properly. The James Webb Space Telescope quickly produced exactly that kind of moment. Before Webb began sending data, astronomers had models of how the early universe should have looked. They expected the first galaxies to be relatively small, messy, and primitive compared with the mature galaxies seen later in cosmic history. Over time, through growth, star formation, and mergers, those galaxies would gradually become larger and more structured. But some of the early observations hinted at something surprising. Webb detected galaxies that seemed brighter, more developed, and in some cases more massive than expected for such an early period after the Big Bang. These results did not necessarily overturn everything scientists knew. But they did raise a serious possibility. Perhaps galaxies formed and evolved more quickly than many previous models suggested. This is one of the most exciting roles of a telescope like Webb. It does not exist merely to illustrate established ideas. It exists to test them. If reality turns out to be stranger than our predictions, then the telescope has done exactly what it was meant to do. The phrase "too early" can sound dramatic, but what it really means is that scientists saw structures that challenged their timing expectations. In the early universe, matter had to gather under gravity, cool, form stars, and begin organizing itself into galaxies. If Webb is seeing systems that already look well developed, then researchers must ask whether the timeline was faster or whether the observations are being interpreted in ways that still need refinement. This is how knowledge grows, not through certainty alone, but through tension between theory and evidence. A telescope shows something unexpected. Researchers examine the data. They compare models. They test assumptions. They look for alternative explanations. Sometimes the old model survives with adjustments. Sometimes a deeper change is needed. For the public, these discoveries can sound like contradictions. But for science, they are invitations. The early universe is no longer just a broad outline inferred from limited data. It is becoming a richer, more detailed, and perhaps more surprising place. Webb is opening that era to closer inspection, and in doing so, it is showing that even our best cosmic stories may still be incomplete. There is something deeply human in that. We build an instrument to answer questions, and it returns with new questions we did not know how to ask. The universe, even in its earliest visible chapters, remains capable of surprising us. How Webb studies the atmospheres of exoplanets. Although Webb is famous for its deep images of distant galaxies, some of its most fascinating work happens on a much smaller scale. Not smaller in significance, but smaller in the subtlety of the signals it studies. One of those areas is the observation of exoplanets, planets orbiting stars beyond our solar system. Exoplanets are difficult to observe directly. They are usually overwhelmed by the brightness of the stars they orbit. In many cases, astronomers detect them indirectly. One common method involves watching a star carefully and noticing the tiny dimming that occurs when a planet passes in front of it. This event is called a transit. For Webb, a transit is an opportunity. When a planet passes in front of its star, a very small portion of the starlight filters through the planet's atmosphere before continuing toward the telescope. That filtered light carries information. Molecules in the atmosphere absorb certain wavelengths and let others pass. By analyzing the resulting pattern, scientists can infer which molecules are present. This technique is incredibly delicate. The signal is tiny. The planet is far away. The amount of light involved is often very small, yet with enough sensitivity and precision, Webb can detect atmospheric fingerprints from worlds many light years away. Why does this matter? Because an atmosphere is more than just a layer of gas. It is a record of planetary conditions. It can reveal temperature patterns, cloud properties, chemical composition, and possible processes taking place on the planet below. Some atmospheres are thick and hot. Some may contain steam, methane, carbon dioxide, or strange metallic vapors. Some worlds may be swaddled in clouds so dense that little can be seen beyond them. Others may have clearer spectral signatures that tell a more detailed story. Through these observations, exoplanets stop being abstract dots in catalogs and begin to feel more like places. Not places we can visit soon, perhaps not ever, but places with weather, chemistry, and physical character. Webb helps transform them from detections into environments. And perhaps most importantly, it extends the search for understanding far beyond our own solar system. It tells us that planetary science is no longer limited to the handful of worlds orbiting our sun. It now includes remote planets circling other stars, each with its own atmospheric identity, waiting to be read in light, detecting water, methane, and other molecules on distant worlds. Once Webb collects light from an exoplanet transit, the real work of interpretation begins. Scientists examine the spectrum, looking for patterns where certain wavelengths are absorbed more strongly than others. These patterns act like signatures. Different molecules interact with light in different ways, and that means a spectrum can contain clues to atmospheric chemistry. This is how researchers can identify substances such as water vapor, carbon dioxide, methane, and other molecules in the atmospheres of distant planets. They do not see oceans or clouds directly in the ordinary sense. Instead, they read the chemistry encoded in the passing light. Water vapor is especially interesting because water is such a central ingredient in our own understanding of life and habitability. Detecting water vapor does not mean a planet is habitable. Many hot and hostile planets can still contain water in vapor form, but it does tell scientists something important about the atmosphere and the planetary environment. Methane is also intriguing. On Earth, methane is produced both by geological processes and by biological activity. In exoplanet science, methane alone is not proof of life, but its presence contributes to a larger chemical picture. Carbon dioxide, too, can provide insight into atmospheric structure, heat retention, and planetary evolution. What makes this remarkable is the scale of the achievement. These planets are often unimaginably distant. The light reaching the telescope has crossed vast stretches of interstellar space. Yet by examining slight variations in that light, humans can infer what gases float above the surface of another world. This is careful science, not fantasy. Researchers must account for uncertainties, instrumental noise, stellar activity, and the possibility of multiple interpretations. But even with those cautions, the achievement remains extraordinary. A species on Earth can now analyze the chemistry of worlds orbiting distant stars. In a more emotional sense, this changes the feeling of the universe. It makes it less abstract. Once distant planets have atmospheres with names and molecules and thermal properties, they begin to feel less like points and more like realities. Webb is helping to build that reality one spectrum at a time. The deep fields, images that look back more than 13 billion years. Among the most powerful ways a telescope can reveal the universe is through a deep field image. The idea is deceptively simple. Point the telescope at a very small patch of sky, one that may appear almost empty at first glance, and collect light from that region for a long time. The longer the telescope observes, the more faint objects begin to emerge from the darkness. Earlier telescopes had already shown how astonishing this method could be. What appeared to be a nearly blank area of sky could, under deeper observation, reveal a crowded landscape of galaxies. Webb has taken this technique further, especially in infrared, and the results are extraordinary. In its deep field observations, the telescope reveals countless galaxies packed into small regions of space. Some are relatively nearby by cosmic standards. Others are so distant that their light began traveling toward us more than 13 billion years ago. Each tiny shape in the image may contain billions of stars. Each faint arc or reddish smudge may represent a system that existed when the universe was still very young. These images are beautiful, but they are also scientifically rich. Astronomers can compare galaxy shapes, brightness, colors, and redshifts. They can study how galaxy populations changed over cosmic time. They can investigate the relationship between young galaxies and older, more mature systems. They can also examine the effects of gravitational lensing, where the gravity of massive foreground objects bends and magnifies the light of more distant galaxies behind them. There is something especially calming about the deep field idea. The telescope stares patiently at one small patch of darkness, and the darkness turns out not to be empty at all. It is full of structure, depth, and ancient history. What looked blank becomes populated. What seemed still becomes dynamic. The universe, under enough attention, reveals abundance where emptiness was assumed. Deep field images remind us that our first impression of the cosmos is usually incomplete. The sky appears sparse because our eyes are limited. The universe becomes richer as our instruments become more patient. Webb is perhaps the most patient eye we have ever placed in space. Why Webb might one day help search for signs of life. One of the most compelling scientific questions of all is whether life exists anywhere beyond Earth. The James Webb Space Telescope was not built as a direct life detector, and it cannot simply point at a planet and confirm living organisms. But it can do something extremely important. It can examine planetary atmospheres in enough detail to identify combinations of gases that may deserve special attention. Life changes atmospheres. On Earth, for example, oxygen is abundant, largely because of biological activity. Methane can also be produced biologically, though it has non-biological sources as well. The most interesting possibilities often involve not one molecule alone, but a combination of gases existing together in a way that may be difficult to explain without active replenishment. This is where Webb becomes part of the larger search. By studying exoplanet atmospheres, it can help identify worlds that are especially interesting for future follow-up. A planet with a certain temperature range, a particular atmospheric structure, and suggestive chemistry may not prove life exists there, but it may become a high-priority candidate for deeper study. This process requires caution. Nature can produce surprising chemistry without biology. False signals are possible. Data can be limited. Scientists therefore move carefully, testing interpretations and considering multiple explanations. Even so, the ability to ask these questions with real data from distant worlds is a profound change from the recent past. For most of human history, the possibility of life elsewhere was philosophical or mythic. It belonged to speculation. Now it belongs increasingly to measurement. Not because we have the final answer, but because that instruments like Webb allow us to study the atmospheres of real planets around real stars. There is a quiet dignity to that kind of search. It is not loud or cinematic. It is patient. It waits for transits, gathers photons, studies spectra, and weighs evidence. It proceeds by caution and curiosity rather than certainty. And perhaps that makes it even more beautiful. The question is enormous, but the method is gentle. If one day evidence of life beyond Earth begins to emerge, it may not come first as a dramatic image. It may begin as a spectral anomaly, a ratio of gases, a strange atmospheric combination that refuses to make sense under lifeless chemistry alone. And if that happens, telescopes like Webb will have helped open the path. What Webb might discover in the future. As extraordinary as Webb's achievements already are, the telescope is still in the early years of what could be a long and productive mission. That is one of the most exciting things about it. The observatory is not a completed story. It is an ongoing one. In the coming years, scientists will continue using Webb to study galaxy formation, star birth, black holes, planetary systems, and exoplanet atmospheres. Some programs will focus on very specific targets. Others will survey broader populations of objects, looking for patterns that can reshape our understanding of cosmic history. It may help clarify how quickly the first galaxies formed. It may reveal more about the role of dust in early star formation. It may uncover planets with unusual atmospheric chemistry. It may observe young planetary systems in the act of formation, showing how disks of gas and dust turn into worlds. It may even detect entirely unexpected phenomena, the kind no one had fully predicted before launch. That possibility matters because major instruments often become most valuable when they reveal something their creators did not anticipate. A telescope is built with goals, but the universe is not obliged to limit itself to those goals. Webb may answer old questions and create new fields of inquiry at the same time. For the public, its future also includes something more subtle. It will continue to change how people imagine the universe. Images from space telescopes do more than support research. They alter perspective. They remind us that the sky is not a flat backdrop, but a layered history of matter, light, and time. They show us newborn stars inside dust clouds, galaxies assembled from ancient light, and distant worlds whose atmospheres can be studied from across interstellar space. Floating far beyond Earth, Webb goes about this work without drama. It does not announce itself. It simply points, waits, measures, and sends back data. Yet from that quiet discipline comes a new map of reality. Perhaps that is the most fitting thing about the telescope. It was built to study the silent universe, and it does so in silence. A gold mirror in the cold darkness, watching ancient light arrive after journeys of billions of years. And with every observation, it expands a little more of the darkness into understanding.